All right, so welcome for our next speaker. This is Tony Edgin from University of Arizona. He's going to talk about more than just load balancing iRODS using HAProxy.
Hi, so you said I'm Tony Edgin. I actually work for Cybers, which is, I don't know what to call it anymore. We're a thingy that provides cyber infrastructure for scientific research, and our core for data, we use iRODS for data management. I'm not going to talk much anymore about what we do, but feel free to ask me. So, HAProxy. Well, actually, I should not just HAProxy. There have been few notable attempts for bringing load balancing to iRODS in the past. And like the HARE system by Yutaka Kawai and Adil Hassan. And then based off of that, Justin James showed how to use HAProxy to do load balancing. You looked up, did I wake you? So I'm not going to focus on high availability. Actually, this will probably be the last time I say those words. I'm going to work on showing you the other things that HAProxy can do with other proxying things it can do, like routing connections based on information inside the TCP packet. And there's some neat, novel things you can do. So I learned through examples, so I'm trying to, this is going to be a bunch of concrete examples, and I'll try to explain things in them that are relevant to HAProxy. And hopefully, if you don't know anything about HAProxy, you'll learn a little bit. And if you know a little bit, you'll learn a little bit more. But in no way will you be able to, an HAProxy expert when I finish. I'm not. I'm a beginner, and I'm with HAProxy still, so I got a lot to learn. So the basic setups, like other examples, it's a client that's going to talk to the proxy, which will then direct traffic to the server, the CSP or IES for old-timers like me. What's different, though, in most of the examples, the resource server connects back through HAProxy. Well, that would unnecessarily complicate the rules for the example, so I would just have the resource server connect directly to the other server, the CSP. There's only one, so it doesn't matter. So versions of software I've used in this, we're still using iRODS 4.1.10, and for HAProxy we use 1.8.4. What is it? I had brain dead there. Just move on. Hopefully it'll come back. So about the examples, oh yeah, now I remember. I wanted to say that all of the examples that were written were actually run on machines. If they're not ones we actually use in production, I at least ran them somewhere. But having said that, now because of slide space, and I've simplified them way down, so I did not necessarily run all the simplified ones. So hopefully they would work. So as I present the examples, they're all going to be HAProxy configuration files, with the fragments of them at least, with the first one being a complete one, and then the fragments should be just modifications of prior examples. Since, as I said before, I'm still a beginner with HAProxy, so I'm not going to give detailed introduction to syntax, but there's a hyperlink there for anyone who wants to learn more about it. Also inside the examples, some of the syntax gets verbose and messy, so I'm using a Jinja templating to encapsulate the complexity, and I apologize for having a level of indirection there, but the slides were unreadable without it, and so hopefully it will be more clear. But the templating is definitely not required for HAProxy. HAProxy has no understanding of Jinja at all. So I'm going to work through 6 examples to introduce concepts. The first one, handling reconnections, and then logging applications and who's using them. And that's basically, that's where the meat one that's going to show how to get information out of the iRODS connection and start beginning to make decisions with it. The next one is going to reject port scanners, and so a motivating use case for this is, well, a motivating reason for this is, well, at least for us, when our ports get scanned by college kids or at the university, and they say, oh, what's connected to this? What's connected to this? Well, you end up with a bunch of crap in your iRODS logs, and this will keep the crap out, at least from that crap. So the example I'm going to cover after that is kind of a harsh one. It's rejecting connections based on a client's username for, well, but we're basing on concurrency limits. So if they connect multiple times, after a certain threshold, you say, well, you've got 6 open connections. The 7th one, you just say, no. So that's not a great example. It's a little mean, but the purpose is to show you how to make decisions based on the information. And the next example, though, is more interesting, and this is one we do use in production. So it's throttling connections for the same reason, based on a concurrency limit, but not using the name, it's using the IP address. So we have high throughput computing systems like OSG. Well, people run jobs on that access our data store, and since these jobs can fan out to thousands of machines at once, you can get in situations where you have hundreds of connections simultaneously to the data store, and that it's basically DDoS. And it really, you can use HAProxy to throttle that, to gate it so only 100 can come through at a time, and the rest will stay in a waiting state and queued up. The final example is we're going to protect the latency quality of service for a select set of IP addresses. Yeah, I mean, one example is more selfish ones, or I should say the more devious one is you find your boss's IP address, then you say, okay, they're always going to have fast access. Everyone else gets throttled. A better example, though, is we also do training workshops, and it seems like whenever we do training workshops, our other users get really active in slowing down our iRODS instance, and that impacts the workshop. So what we can do is we can set up a select set of IP addresses that the workshop users will use, and they will get direct access where everyone else gets throttled. So let's get to the examples. So to the right is a very simple HAProxy configuration file. It should work, although I would never put this one in production. It's in this section we're going to change. The relevant information I wanted to tell you about it, though, is HAProxy thinks in terms of front ends and back ends, and you can think of it as clients connect to HAProxy. They're actually connecting to a front end at HAProxy. HAProxy, when it connects to the server, it uses a back end to connect to the server, and in the middle, there's routing. And that's where decisions get, well, the front end has logic in it to decide which back end to use, and the back end has logic for, it tells what server to go to. Now, HAProxy also has, mentioned throttling. Well, how it does that is through the max con term. You see in the back end there for the single server. We're allowing 200 connections through at a time. So what it does with the extra connections is it queues them up and then sends them through in order as slots of open up become available. Now, one thing, now back to the real purpose of the thing, handling reconnections. So in the other examples, they talked about proxying. They never talked about reconnections, and I didn't know this, but when an I command requests a reconnection like the iput-t option does, it reconnection information comes from the server back to the client saying, okay, here's the host to connect to, here's the port to connect on, the higher, usually the 20,000 series ports. Well, a lot of the I commands, at least the ones I played with, ignore that, and they reconnect right back to the same host they connected to originally. So then they, instead of connecting back to the server directly, they connect to HAProxy. Well, if HAProxy isn't listening on those ports, your connection breaks. So this can be a feature, though. It's not a bug, necessarily, because you can now, your throttling is more accurate now, because the reconnects still have to go through the throttling process. So they count towards the total 200. So then you won't, if you have a lot of reconnects now, you won't have like 215 on your server. You will still be limited to 200. Okay, on to the next. So logging, and here's where the Jinja comes out. It's the basic templating syntax is the double curly braces with a name in there. And I tried to make it stand out a little bit more by making it italics. So I'll work through to try to explain what's going on here. So we have a TCP request thing, the statement in the front end, and content and capture. So this means inspect the TCP packet, capture based on what's in the Jinja templating, and store it in a capture request header variable. So in those, if you have multiple captures, they just basically, the second capture gets the first header, well, the one header, I don't know, the index 1, so they say. The third gets the second, and so on. And so then you can reuse those further down in your expressions. So that an ACL, it's a named thing in there, that it's a named Boolean expression, and that you can use to make decisions. So this one we have isCon. It's basically, if the first capture contains the string rods connect, evaluate to true. And then basically, we can use that in our other content captures where we capture the option, the client user, and the client RCAT zone from the connection. I'll tell you more about how RODS connection format in a little bit. But anyway, we're using the ACL to make decisions if we're even going to inspect those. And then we have our log format, which is also using those. And it's basically, I'll tell you more about that in the next few slides. So let's interrupt the example and talk about what the RODS connection string looks like. So it's basically 3 parts. The first 4 bytes are as a binary, well, it's a number. It tells you the size of the next part, which is the message header. And the message header is an XML element of, well, in the documentation, it's a message header PI ACAT instruction. And then following that is a startup packet XML element. And the header has very minimal information that we're interested in, but the startup packet has the real meat. So if you want to learn more about that, there's a link to a paper that describes a lot more. So here's the interesting bits for us. The message header, the only thing we're really interested in is the type element, the type field, and it can take on one of several values. The one we look for is RODS connect. So the startup packet has lots of interesting fields, and there are even more than I've listed. But these are the ones I can think are immediately useful. And the ones we're going to look at in particular are the client user name, the client RCAT zone, which is the client zone, and option field, which often holds the application name. So that's how IPS figures out that it's an IPUT statement or an IGET or anything else. So back to our example. So let's look at the expanded Jinja a bit. So the message type capture uses the request payload LV, which basically this says take the first 4 bytes and use that to tell how much data to read next. So that it reads a certain amount. Then pass that through 2 filters. One's the first filter removes all the information before the value of the type field. And the second one removes all the information after it. So all you're left with is the value, hopefully is RODS connect. Okay, and so these, this time I used a macro. Ginger allows for reuse, that's anyway. So this one also looks at the packet, but instead of, we don't know, since we don't know exactly where the startup packet begins, we take the whole thing after the 4-byte integer, and read it to the end. And that's, so you see it's a request payload without the LV this time. So this just says, ignoring the first 4 bytes, read to the end of the TCP packet. Then strip what's before the field of interest and strip what's after it, kind of like what we did previously. And what's left should just be the value of the field. So finally, we log it. So the first header one is recorded in the option field. The second one is the client user's name. The third is the zone name. And when we log it, we're also we're going to prefix it all with the %CI, which just means the client's IP address. So we're going to log client IP address, application name, and the client user with, in the standard iRODS form, username, pound, zone name. So that shows you the meat of extracting the information from the iRODS header. iRODS connection header. So on to the next example, rejecting port scanners. So this is really simple. Basically, you use the ACL we previously defined. Then the last thing is we just reject it if it doesn't contain the RODS connect string. So on to the next. And this is the one about rejecting users based on concurrency limit. So concepts here that are interesting is the stick table. A stick table, it allows you to keep, it allows one connection to in C state across all the connections. And then you can do things like track how many of these connections are actually from the same host or the same username, etc. So in this one, we're storing something called concur, which means just the number of concurrently open connections from our user. And we've set it up so that we're going to be storing name, pound, zone in the table. So it will be a map, so just be a name mapping of name, pound, zone to how many times that shows up in open connections. So how we get the data into the track table is through the content, the third line from the bottom, which is content track SC1. Do I have a cursor? Oh, hot dog. No, I have a pointer. So SC1, track SC1 means store what comes after that, which is the capture request header concatenated with the other one, in the counter SC1. And use that as a counter for it and into the stick table. It's very confusing nomenclature. There's no way explicitly it says this is for that table. It's just, it's the way HAProxy works. So anyway, now our ACL is, if too many connections, if the SC1 counters that points to a concurrency, concur, that's greater than 1, then since That's our ACL. We just do the content reject again at the bottom if there's too many this time instead of if it's not a connection. Okay, unfortunately, this only works in HAProxy 1.9 and newer, and we're using HAProxy 1.8 because that's the one they consider in long-term support, so it's more stable. So how you do that in 1.8 is you have to make an assumption about the packet that comes across from iRODS, well, the client. So you have to assume that the client zone always comes after the client user when you do your extraction of the information from the packet. And so you can see down here the UZ capture. You do the strip before client, do some stuff to strip between client and RCAT zone, and then strip after RCAT zone. So if those come in a different order, we're all of a sudden going to get garbage. That's the 1.8 solution. Now this is one of the ones we have in production, and the throttling usage based on IP address concurrency. So what we do here is we have the main backend, front end, excuse me. It can route to the main backend, but it can also, what it does now is it routes to a second backend we have set up called iRODS throttled. And then this backend has a max con set to 100 instead of the 200 typical. So it limits, well, it's only 100 to pass through its gate onto another front end we've defined, which then directs traffic right back to the back end. So basically we've just got a queue off to the side, route connections through, and we'll only let out 100 of them pass through this thing at a time, and then they come back onto the mainstream. And here's what it looks like goes off the end of the screen, but that's actually the end of it. So internally, we're going to use a Unix socket this time for the iRODS throttle backend. And then we're going to set up the second front end to listen to our Unix socket. So that's one of the neat things of HAProxy is it can proxy for itself. So in effect, we've set up two different proxies here. We're just passing all those connections through a second proxy, all the extra connections for users. So protecting latency, this is the workshop example. So it's very similar to the throttle one, except you reverse it. Now the main flow goes through iRODS throttled, and the exceptional few just go direct. So you don't want to overburden, put too much burden on your normal user who's not in the workshop. So I would set the max connection very close to the overall max connection. So I've set to here 80%. And this allows for like 40 workshop users to come through at all times, even if your normal users are getting very, very active and up to 200 or 300 users. This will not impact, the workshop will not be impacted by that. So I think it's fairly obvious. What you do is, in this case, you create a file. I've called it fastpass.lst, and you list the IP addresses in it that are protected. And you can list both single IP addresses and IP address ranges. And the ACL with the source term means the source with a -f means use this as a file for defining what a source is. And then this just says, let me reread this. Basically, this means if the source is in this file, the source being the client's IP address that's incoming the new connection, then it's a VIP source. And then you can use the backend for them. Otherwise, the default backend was throttled, so it just goes through the throttling process we talked about. Hey, wow, that went a lot faster than I planned. So any questions?
Yes, here it comes.
So in that particular setup, which is great by the way, and I'm going to be implementing it when I get back, what happens to localhost connections?
If you could treat them like normal IP addresses, and I guess I'm not understanding the direct question. I think nothing. I think it would know it's a localhost connection at this level. It would just see if 127.0.0.1 or 10 or whatever you're using. If you had it connected another way, it's like through a socket, so you were actually connecting through a Unix socket. You probably just have to set it up differently.
I think the use case of so many people connecting that you couldn't run IPS yourself to find out who's connecting to tell them to stop doing that.
Oh yeah, that's one of the things I'm looking into. That there's ways you can set up HAProxy so that it passes the client. It pretends to be the client when it passes the packet onto the server. That's using the HAProxy, Linux HAProxy thing. And there's also the proxy protocol that's HAProxy was instrumental, helped create. And if we could get iRODS to understand the proxy protocol, then that information would come across in the TCP itself, instead of having to do the spoofing. So that's one possible hackathon topic.
Thank you.
Anybody else? All right. Thanks, Tony. Very good.